I'm Doug Wicks, the program director at ARPA-E. I'm here to talk to you today about the idea of waste not, want not, or can we eliminate tailings from mining? Sustainable energy is going to be enabled by minerals. When we take a look at solar, batteries, wind energy, these all depend on elements that we're going to mine out of the earth. Examples of those are given on the left, 17 key ones that are going to be very challenging for us to obtain, especially as we look going forward, that over the next 20 years, we're going to see massive increases in demand for some of these minerals in the energy sector. But at what social and environmental cost, we have to ask. We can take a look at the Koniambo nickel mine in New Caledonia. And this mine is expected to grow to 100 square kilometers to supply nickel for the transition. And this is just one of many mines. And we also then can look to Chile, where we have the El Morro copper tailings dam in place. This dam holds back 2 billion tons of water and nickel tailings from the, water and copper tailings from the mining of copper. And we can also then go to Mongolia and the People's Republic of China and see what happens when we mine for rare earth elements. These materials that are key for our displays and our magnets. The waste piles go as far as the eye can see. So keep in mind the scale of mining is almost incomprehensible, even now, before the energy transition. Yearly, we're going to mine about 19 billion tons of minerals to go into the economy. At the same time, that mining produces more than 50 billion tons of waste. To put that into context, think about a train that has 500 million carloads of waste. That's the size of the waste issue we have. And we're going to be adding that waste to an existing waste in piles and dams that exceeds 500 billion cubic meters. This is larger than Lake Erie in the United States. So keep in mind the energy for the minerals for the energy transition are among the worst. We look at these, we have tailings per ton of metal that go anywhere from 1 million tons of tailings for every ton of metal, down to 99 tons of tailings for each ton of copper that we mine. And keep in mind that also as we go forward, the growth for these is going to be astronomical. We're going to be needing 6 billion tons of these to transform the grid. And we're now on course to leave a 1 trillion ton legacy of waste for the next generation. So when we come back to the idea of zero waste, this is really only a dream. The reality is current mining practices are laser focused on a single metal. When we go after copper, we just take the copper out of what we mine out of the ground, and we leave mountains of waste behind. But this waste actually contains elements that are mined elsewhere. If we take a look at a tailings pile in the Philippines from the mining of copper, we find that it contains a large amount of elements that we're already mining from other locations. This includes silicon, aluminum, iron, magnesium, and titanium, all critical minerals for our energy transition. So there has got to be a better way to go forward with this. So the road to reducing tailings. We need processes to refine almost everything that's taken from the earth. So instead of just focusing on a single metal, can we develop processes that address a secondary metal, a tertiary metal at the same time, and perhaps repurpose this material that's left over into building materials, all the while greatly reducing waste? And another benefit of these second two areas, we could actually use building materials and waste as a sink for carbon dioxide capture. So going towards zero tailings, what do we need from you, the scientific community? We need integrated refining approaches that use all the materials. We need reduced land, water, and power requirements for the minerals we mine. And we need to use the leftovers for something beneficial, not just a waste pile. So keep in mind that clean mining is key to the sustainable energy transition. Now is the time for innovation. We have a need for increasing supply while decreasing impact of this mining activities. And with that, I would like to say thank you and turn the talk over to Halle Cheeseman.
Hello, my name is Halle Cheeseman, and I'm talking to you today about fishing for riches. By the end of this presentation, each and every one of you will know how to go and find $10 million. We're also going to be solving this puzzle. How would you go find the critical metals for Tesla using puffables, wiffables, bicycle chains, and as much ocean seawater as you can collect? Some of you will know I spent most of my career in batteries, and batteries require metals. We have lithium ion that needs lithium, cobalt, nickel, and manganese. We have a vanadium redox flow battery. We have special batteries that need silver and magnesium. We have AA's batteries, zinc, manganese, and potassium, and people are working on larger versions of those. And finally, we have zinc bromine flow batteries. It's EVs that are going to increase the demand for metals more than anything else. So over the next 10 years, we see a factor of 5 increase in the sales of EVs. And while we're going to enjoy significant CO2 emission reduction as a result of that, we are going to need a lot more metals than we use today. For batteries, we see some significant increases, and even against the base of existing applications, substantial increases with cobalt at 2.4 times, lithium at 3.7 times, and even nickel, where there is a base today of 2.7 million tons a year, is going to have to increase to 4 million just because of battery demand. As we wrestle with supply challenges, we have to be cognizant of the social and political issues related to some of the countries where some of these materials come from, and the issues relating to cobalt have been well documented. So let's go and fill a football stadium full of seawater. I chose the Dallas Cowboys Stadium, and we snuck out at nighttime so nobody would notice, and we filled it with 2.8 billion liters of seawater. From that, we're able to obtain a whole bunch of minerals, excluding sodium chloride, 4,000 tons of minerals worth over $10 million. And you can see magnesium, bromine, potassium, lithium leading the stack here. So that's your $10 million. Find a hose, pick your favorite football stadium, and go start collecting your money. Of course, it's more complicated than that, and the ocean is a little bit bigger than a football stadium. A lot going on this slide. We have part per million, part per billion, part per trillion on the left-hand side, the total quantity of minerals involved on the right-hand side. We have price along the bottom, and I've colored here the elements in green that are the most economically feasible and the ones that are in red that are least economically feasible. The ones in yellow are in between, and you will notice uranium, another key element for our future energy needs. Folk have already been working on this. The work started in Japan and has continued in the US, and we see now the puffer ball and the wiffle ball reunited, along with some bicycle chains in the bottom left. This was work carried out by Mahahaji to demonstrate that indeed using a material called amidoxime that coated the puffer ball, that uranium could be extracted from seawater. The same group did some paper studies looking at existing but deactivated oil rigs in the Gulf of Mexico, and demonstrated that it might be possible to extract over 1 million Tesla vehicles worth of cobalt per year. And finally, something a little bit different, and this is an ARPA-E project being executed by PNNL, looking at rare earth metals, which are important for electric motors, and their possible extraction from macroalgae. Of course, cost is going to be the key issue here, and I chose an example on the left to illustrate this. We have our lobsterman who has a whole bunch of costs, but the key thing that drives his economic feasibility is how many lobsters does he catch? And on average, the lobsterman catches 2 per trap, takes us back to the dock and gets $9 for them. We can't yet enjoy them, of course. They had to be prepared, whether that's steaming or grilling or baking or whatever. Similarly, with fishing for minerals. We have to collect them. We may collect them from the ocean, but brines, estuaries, and effluents are other possible sources. And once we've collected them, we have to separate them or prepare them. We have 4 methods here: a pressure method, membrane, distillation, crystallization, solar, thermal, electrodialysis, electricity, and finally, adsorption, absorption, using the fundamental properties of organic or synthetic materials to selectively collect minerals. Strategies for attacking cost. Increased collection. If our lobsterman got 4 lobsters per trap, his whole economic proposition is wonderful and he can take his holidays early. So if we could increase the amount we were collecting with different materials maybe, that may change the game significantly in this particular area. Utilizing existing structures and covering the cost of mooring could be important for us. Pursuing multiple metals, the folk who went out and looked for uranium also picked up lots of vanadium and magnesium, which they didn't care about. But in fact, if you bundle the 3 together, maybe you get a better economic proposition. This one speaks for itself. And finally, can we focus on more concentrated salty water? So for example, the water that enters a desalination plant actually leaves that plant at double the concentration for what's not used. So here's my final slide, a vision for plentiful and responsible supply. Once upon a time, we, the US, were a leader mining on land. This is an opportunity maybe for us to be a leader extracting minerals from seawater. This is, though, the great equalizer, because 80% of the world's countries have ocean access. The ask today is, we want your ideas, suggestions, and innovations in the areas of absorption, filtration, and separation. So come and talk to us, come and have conversations with us, don't be strangers. And to that effect, my contact details are on the bottom. My concluding sentence is borrowed from Harry Truman. There is enough in the world for everyone to have plenty, to live happily, and to be at peace with his neighbors. Maybe the ocean can help us achieve that. So thank you for listening. Go collect your $10 million. It's now my pleasure to hand over to Dr. Elizabeth Troein, who's going to be talking about extracting minerals from other interesting places.
Thanks, Halle. My name is Elizabeth Troein, and as a biogeochemist, I'm always on the lookout for natural mechanisms that can inspire clean energy technologies. Today, we will dive into metal accumulation by plants, and I'll work to convince you that plants should be doing our mining for us. Conventional mining is a highly energy and emissions intensive process. It involves digging up, grinding up, and extracting metal from huge amounts of rock, sometimes extracting as little as 0.1% or less of that rock for use. But plants such as these have evolved to be extremely efficient at breaking down rock to extract nutrients for their growth, and they can accumulate metals to high concentrations. So maybe the future of mining looks more like this field of metal accumulating plants, and perhaps plants could extract and create economic ores in the United States in places that they don't currently exist. A number of plants have evolved to grow on soil that is dry and rocky and rich in metals. These environments include soils that form on ultramafic bedrock or igneous rock that is enriched in a number of heavy metals compared to other rock types, as shown here. Here, plants have evolved to grow on the thin soil that covers the fresh, barely weathered bedrock that is rich in metals such as cobalt, nickel, iron, manganese, and magnesium. These plants have evolved to have low water and nutrient requirements and can withstand the high metal content of the bedrock that has not yet been leached of its metals. This is in contrast to plants that are endemic to areas with well-developed, more fertile soil, which require more water and nutrients and will only tolerate soil that has been leached of metals through natural weathering processes. Some of the plants that grow on metal-rich soil are hyperaccumulators, which means that they take up metals from soil at faster rates than other plants to reach metal concentrations that are often much greater than the soil content. The shrub shown here, which grows on the ultramafic soils of New Caledonia, accumulates up to 25% nickel citrate in its sap. This metal uptake is in part a way for the plant to detoxify the metal by converting it to a form that the plant can actively manage, and in part a way to deter pests with a metal concentration that is toxic to most organisms. There are a number of metals that plants accumulate which are necessary for clean energy technologies, including cobalt, nickel, and manganese for electric vehicle batteries, and rare earth elements for wind turbines, for example. As the global demand for metals continues to rise, we are depleting the concentrated ores that we are currently mining, and mining is becoming more expensive and also more energy and emissions intensive. Many US ores are currently lower grade or lower concentration than the non-US conventional ores listed here, and are thus less economical to mine. However, the metals that are required for clean energy are distributed throughout the Earth's crust and across the globe. In the case of cobalt, which we will focus on as an example, 70% of cobalt production currently occurs abroad in areas of conflict. However, there is enough cobalt located in the United States, in just the top layer of Earth, where roots can theoretically reach, in just the surface deposits of metal-rich ultramafic rock, to satisfy the current rate of US cobalt consumption for at least the next 100 years. That is, as long as we can concentrate this cobalt for ease of extraction, perhaps with plants. Flowering plants in the mint family, similar to the one shown here, have been observed to concentrate cobalt up to 1% in plant biomass as organic acids. If biomass is turned to ash, this cobalt can concentrate further to about 10% in the form of cobalt oxides. These oxides can then be purified or reduced to form a metallic cobalt. So since there is evidence shown here that plants can concentrate cobalt from rocky soils, mining with plants may work, but will it matter? Let's dive into an estimate of the potential scale of plant-based mining that is possible in the United States. Let's imagine a field of cobalt hyperaccumulators the size of Rhode Island, which is equivalent to just 0.2% of the land administered by the Bureau of Land Management. In this field, there is enough cobalt in the top layer of Earth where roots can potentially penetrate, and the plants have been observed to grow at a fast enough rate in nature to produce upwards of the 10,000 metric tons of cobalt consumed in the US each year. This level of production can likely be maintained for about 10 years before the surface soil is depleted of cobalt. This bio-based mining also has the potential to be carbon negative, up to 1 million tons of CO2 per year based on rates of photosynthesis. There's the potential for additional CO2 drawdown for the silicates that are weathered to form carbonates as the plants break down the rock. Additionally, this land will explicitly need to be land that cannot support food crops, since it must have a high metal content. The potential sites would include surface ultramafic rock formations shown on the map here in red. Over time, as the hyperaccumulators take up metals and hasten the weathering of rock into more fertile soil, these processes have been shown to detoxify natural asbestos deposits, such as those located in former asbestos mines shown as X's on this map. Thus, bio-ore-based mining has the potential to be a win-win situation for both carbon negative mining and land reclamation. For the potential future of plant-based mining, I'm envisioning an engineered plant that optimizes all aspects of metal accumulation observed in natural species. For instance, we can divert as much fixed carbon as possible into organic acid and metal chelator production to enhance the breakdown of rock, similar to mechanisms employed by lichens that colonize fresh bedrock. We can also upregulate phytolith or plant rock formation. Phytoliths are silica particles that precipitate inside plants to strengthen them. If more silica is taken up by the plant, the silicate-based bedrock will break down faster. We can also select and optimize metal transporters to increase the concentration of metal in the plant and control where the metal is located within the plant, as well as the chemical form of that metal to ease metal extraction. So are lush green hillsides the future of carbon negative mining? To achieve carbon negative mining today, we might think about how to offset emissions from conventional mining with direct air capture and carbon storage. But with bio-ore, perhaps the future of carbon negative mining will look something more like this, where plants create economic US-based ores, plants draw down CO2, and plants increase long-term carbon storage. I'd like to start a conversation on what we can achieve with bio-ore. Do you have thoughts on how to grow the most efficient and economic bio-ores, including genetic controls or geographic areas to target? If you have ideas or potential innovations in plant-based mining, please reach out. I look forward to hearing from you. Thank you, and now I'll hand it off to my colleague, Dr. Joseph King, who will be telling us more about long-term carbon storage.
Thank you, Elizabeth. That was excellent. Waiting to exhale almost sounds romantic. Unfortunately, what I'll be talking about today is anything but that. I'm Joseph King, and today I'd like to talk about carbon sequestration, our current path, a few of my concerns, and the enormous opportunity that lays before us. If you've read any of the recent overviews, downhole sequestration plays a major role. Among these, there's strong interest in using spent oil and gas wells. probably the cheapest and easiest storage solution. But for me, not a great solution. Their logic is simple. These reservoirs have held oil and gas for millions and millions of years. So why not reuse them for CO2, right? Well, my concerns are equally as simple and not so mainstream. We've ruptured the diaphragm. We have limited knowledge of where the abandoned wells are. Gas plumes continue to migrate. The plugs won't hold. And our history with long-term maintenance of containment systems is not very good. So let's take the first two. 150 years ago, the cap rocks were pristine and impermeable. Since that time, we've plunged thousands to millions of holes into it. And that's not the problematic part. The NETL and the EPA estimate there are between 3 million and 20 million abandoned and orphaned wells, in addition to those in production today. Now think about that, 3 million to 20 million. That's basically admitting we don't know how many there really are, and worse, where they are. Next two concerns. Say we leverage the oil industry's experience with using CO2 for enhanced oil recovery. They generally see an increased production in the 4 or so wells surrounding the injection point. Basic path of least resistance. So just plug those adjacent holes and be done with it. Well, if you impede the gas plume, it just spreads further and further out. Now you have tens to hundreds of holes to plug. The more you pump down, the bigger the plume, the further it spreads. Nature finds a way. So say we could plug all the holes, even the ones we don't know about. The cements used only have a useful life of roughly 50 to 70 years. They're just brittle materials that naturally crack and degrade over time. In air, CO2 actually accelerates this degradation by a process known as carbonation. Pure CO2, liquid or gas, is 2,500 times more concentrated, so it should react even faster. Supercritical CO2 at over 1,000 psi, faster still. Now let's look at a few examples of our history with containing dangerous materials. A coal ash breach in North Carolina, a massive heavy metal poisoning of a river in Colorado, an infrared shot of the Elisa Canyon gas spill outside LA, and Deepwater Horizon spill in the Gulf. You can go online and find hundreds and hundreds of such containment failures. Absolutely nobody wanted these to occur, but they did, and they will. So since nature always finds a way, we need to find a way to take humans out of that long-term equation. That's why a number of us believe that the best sequestration approach is something we call accelerated geomineralization. Now, geomineralization was proposed back in 1990 by a very clever geologist named Seifritz. What he figured out was that you can take certain rock types, mush them together with CO2, and get 2 new rocks plus some heat. Here, a simple olivine called forsterite is converted into magnesite and quartz plus heat. Now, the great thing about rocks, they tend not to roam. They lack that Wunderlust common to gases and liquids. Now, that plus heat part is also very important. That means the reaction is exothermic. That's thermodynamic speak for saying it really, really wants to happen. Now, you can formulate these into general equations about which rock types react with CO2. Generally such types as basalts, mafic, and ultramafic rocks, none of which are usually found in oil and gas fields. So you wouldn't expect mineralization to occur there, well, ever. Now, you may be thinking, this all sounds really, really good, except for one little detail. That is, these reactions are generally very, very slow. Really, really slow, like thousands of years slow. So it was really exciting to read reports out of Iceland and our own Department of Energy work at Wallula, Washington, where they saw greatly accelerated carbon dioxide mineralization downhole in the rock types I just mentioned. Not in decades, but in a couple of years. All early stage work, but truly a new hope. Now, there are three types of mineralizations we talk about. XC2, that's above ground formations. Superficial, that's surface debris such as slag and mine tailings. And in situ, which is downhole or below ground. Now, I'm not really interested in the first two, although I have a few colleagues who are. Very, very important, yes, but relatively small potatoes. 100 million ton potatoes each, but we're plowing a 50 billion ton field. In situ is that tens to thousands of billions of tons approach, depending on where you do it. Now, what we need are a few innovative teams that help us accelerate development and commercialization of in situ technologies. Balanced teams might include geologists, they know rocks and where to find them, garden variety chemists like myself to help with enhancement acceleration, drilling experts to help us get to where we got to go, and of course, chemical, petroleum, and pipeline engineers. Always good to have a couple of plumbers on speed dial when you need to move stuff through pipes. So now, if we're serious about removing humans from the responsibility and expense of long-term monitoring and maintenance of carbon sequestration sites, mineralization is the only viable approach. If we continue down our current path of potentially using spent oil and gas wells where mineralization will never occur, each of these sites will merely be waiting to exhale. I'm Joseph King, and thank you for listening. Now on to our question and answer period with the rest of my colleagues from this panel.
All right. Can you hear me? Halle, raise your thumb.
Yeah.
Okay, good. So we have quite a few questions. It seems like Elizabeth is the most popular at the dance, so let's start with her. Elizabeth, is metal accumulation in plants driven by plants themselves or symbiotic microorganisms?
Yes, that is a great question. So plants, for the most part, are driving this uptake of metal. So the metal transporters and the genes involved in transporting the metal from the soil into the roots are specific to the plant, and they are the result of evolution of that plant when it evolved to be able to live on these metal-rich soils, as well as the genes involved in the translocation of that metal, so the transport of that metal from the roots to other parts of the plant where it accumulates. Plants also make their own organic acids to break down rock, and they make their own chelators to break down rock. However, microbes do play an important role as well in the bioavailability of metals in these environments. So microbes also make organic acids and metal chelators. So they will be a very important part of the picture. But I'm definitely interested in the role of plants. They are, they're photosynthetic, so they, don't require sugars, as say maybe a microbe involved in biomining might require. Again, they can sort of, plants can do, in theory, do a lot of this destruction of the rock themselves, again, with the production of acids and uptake of those metals. So hopefully that answers your question. Happy to chat more.
All right, Halle, the next one seems to be for you. For absorption-based systems, do you have insight on how much a new advanced material should cost?
Yeah, there's obviously a number of factors here. One which I didn't really mention during the presentation, which is it reusable? So it may be less about the cost of the material in terms of your manufacturing costs and more about your total cost of use over many uses. So if you were to use it on that base, we need to be down in the dollars per use in order to make the economics work for most of the minerals that we're interested in.
Right, thanks. Doug, Can you speak to some of the technologies you envision for extracting materials from tailings themselves?
It's a fairly wide open area. I think we've seen advancements, but I have great interest in electrochemical approaches that can selectively remove materials and dissolve it. And Elizabeth and I have talked a lot about biochemical processes, and that's something we're already looking at is organisms to remove the materials, or plants. Again, or, going into the macro plants, macrobiology to do it. So there's a variety of methods, and I think most importantly is to combine it with the growing emphasis on the ex situ mineralization of CO2. Combining the two might really be of great interest to us.
Thanks.
I'd like to comment if I may, Joe.
Yeah, go ahead, Halle.
Once upon a time, I was an electrochemist. But I find it very interesting that so many of the things that we're looking to do in the future could involve electrochemistry, and Doug mentioned electrochemistry. I know Christina Chang mentions it in her presentation relating to steel manufacture. And as we look towards more and more renewable energy sources, which are about generating electricity cleanly and hopefully cheaply, then we're going to find electrochemistry see far more use than we do today, which is more about batteries and plating maybe. We're going to see electrochemistry be far more significant. And I'm looking forward to working with Doug and others on the electrochemical options regarding his program.
Great. Elizabeth, this looks like it's for you. How much are the water requirements for plant-based mining compared with conventional mining?
Yes, that is a great question. So broadly speaking, the plants that do, the natural plants that are hyperaccumulators have very low water requirements. So you wouldn't, potentially, that could be something that could persist without irrigation, maybe with further research to see if that might be possible. And additionally, in contrast, maybe to other, say, biomining processes that might require a pool of microbes, I can imagine that the water requirements would be lower. Or additionally, for a more conventional mining process where there would need to be extraction of the metal in say a pool of water. So I can imagine that the water requirements could be lower, maybe could be done without irrigation, just with natural rainwater to these ultramafic soils. But that would be something that would require further research. But I could see the potential for low water requirements there.
Yeah, I'll add in to kind of emphasize that the mining industry and mineral extraction is one of the most water intensive ones out there. And I didn't touch on the volume of water, but it exceeds Lake Erie every year. Very easily for the amount of water that's deployed in mining.
All right. Looks like I get a couple. Are there connections between work on enhanced mineralization and geologic storage in saline aquifers? In a sense, yes. In another sense, no. There are some saline environments where there are certain basalts or glassy formations that will, in fact, mineralize slowly over time. And then even in the basalts that are reactive, like in Iceland, or where Ocean Network Canada is going off British Columbia shortly, those systems have a high porosity, so you need that retention a little bit while the conversion is taking place. The problem with the saline aquifers is they still have a long-term monitoring requirement, and you worry about, will those plugs hold? The advantage they have over traditional oil and gas areas is they're usually singular penetrations into the environment through the caprock. They're not the pin cushions you see, like the shot of Bakersfield that I showed you there, where my sister teaches school. That's a contemporary field that's in operation, and you don't have that kind of thing, especially in deep water environments. I hope that answers your question. I like them better than oil and gas fields, but they're still not perfect. Dr. King, could the heat release from mineralization be useful for other applications? If it could happen instantaneously, yes. But these reactions tend to be, even the ones that are accelerated, metered out over time. So it's the evolution of heat and the kinetics of the chemistry itself taking place that would probably be too slow to give you a useful heat content per unit time. So that would be the limitation that I'd see there, that the kinetics, even with the accelerated geo-mineralization, would not be fast enough to be useful and be very low grade waste heat. Okay, Halle, this one looks like you. What is the overall potential impact on battery recycling on the waste problem? Well, that could be a couple of us, but Halle, why don't you try it?
So the last bit was on the waste problem?
No, the battery recycling on the waste problem, yes.
Yeah. Well, if you look at the increase in demand, we're going to need every bit from recycling as well as new sources. So, I showed a chart that said metals are going to increase in demand by a factor of 5 by the end of the decade. Other forecasts out there are more aggressive than that, higher than that. But certainly by the time you get to 2040, you're talking about an increase in demand for some of these elements, which is 30, 40, 50 times more than it is today. And so, yeah, we're going to have to be recycling stuff. Oh, by the way, that stuff that went into the field 10 years before. Oh, and we're going to need new sources, and we're going to need sources on land and hopefully sources on the ocean too. So I think this is a case of all hands on deck. We need to find every way possible to get these minerals and to help us be as independent as we need to be in order to meet the climate challenge in the future.
Thanks, Halle. I think the next one's for me too. Could carbon mineralization units ever be situated at a CO2 emission source? Or I assume the T is temperature and P pressure important. Oh, there we go. Important to the kinetics. I'll answer the last part first. The answer is yes. Both those have been demonstrated, particularly in the guys working from Carbofix outside Reykjavik in Iceland. They find a profound dependence there in terms of rate increase, but you'd expect that sort of from even general chemistry anyway. On the other case, they are in fact co-located. There are a lot of geothermal sites spread along Iceland, since it's on a nice volcanic rift area. And it turns out that geothermal is not necessarily, or hydrothermal in particular, it gives off a fair amount of CO2 in the actual fluids due to seepage accumulation from the volcanic activity. So one of the things that they want to do is be totally carbon neutral there. So Carbofix is co-located at the geothermal site and is taking that effluent CO2 instead of having them send it off into the atmosphere, and mineralizing it at about, I guess, 800 meters. Not terribly deep, but that's where a lot of the basaltic high porosity materials are that they're going after. So the answer is absolutely yes. Let's see, next one. What would be an impact on ocean mining? Halle, this must be you, on marine, coastal, and ocean ecosystems.
Okay, yeah, this was mentioned actually in an earlier fast pitch, more in the lines of what ARPA-E's approach. As we start to investigate these opportunities, we want to make sure that we bring everybody to the table. So whether that's a NOAA in terms of a government group, or whether that's environmentalists, we need to bring the right people to the table to make sure that we're going to manage the ecological effects properly. Of course, I'm a little bit biased here. I think actually processing seawater is going to be a lot less disruptive to the environment than some of the other things that we've done in the ocean over the years. I was reading an article over the weekend about trawling along the bottom of the ocean just to catch fish. That itself has been arguably very disruptive to ocean life. So I'm a little bit biased, but I think actually taking ocean water and processing it and pulling out the minerals is possibly one of the most ecological things we could be doing in terms of getting the minerals out of the seawater. And even if we supplied all of our needs for the next 500 years out of the ocean, we're only going to reduce the concentration of these elements by 1% or 2%. So our effect is going to be minimal, and that's got to be good for the environment.
Great. Elizabeth, this one is for you, but someone's already creating hybrid programs for you and Halle to work on. Is there the potential for using aquatic plants as a source of bioore?
Yes, great question. Yeah, certainly a possibility and something that's already ongoing to some extent in one of the projects that Halle mentioned in his talk. I think a really broadly, really interesting thing to think about is not only sort of the relative concentrations of the metals in aquatic versus terrestrial environments and how that impacts sort of the kinetics or the profitability of specifically using plants in this context. So in the case of cobalt specifically, you have about 6 orders of magnitude higher concentrations just in bulk continental crust versus the ocean. So that could be something to think about when you're thinking about whether a plant could really accumulate enough metals in an ocean environment versus maybe on land. So definitely a possibility and definitely something that's being thought about, but definitely pros and cons to aqueous versus terrestrial plants to think about.
I'll kind of chime in. The program we have at Pacific Northwest National Labs looking at macroalgae is showing somewhere in the neighborhood of 10 to the 8th increase in concentration in the biomass versus the ocean, very selectively picking up a wide range of not only rare earth elements, but also nickel and cobalt, as a process. And the question is, can we economically do that and process them to make use not only of the minerals, but the carbon that's created, in that from a program such as Mariner.
And certainly,
So Doug,
speaking for me,
go ahead, Hal.
I look at the ocean opportunity and see the opportunity for synthetic materials, like the amidoxines of the world, but also algae. So, I see two overlapping circles there. Oh, and the plant one actually, of course, overlaps with the plant opportunities on the land. So there's a lot of synergies here in terms of pooling our learning and learning together so we can maximize the opportunity that we're looking at.
Okay, Doug, are there logistic challenges to using everything that is mined? Is there going to be an increase in demand in water processing, capital investment?
Yeah, the logistics really come back to, if you look at potential for making construction materials, for example. These are materials that are always produced locally. And so if you have a mine in the hinterlands of, let's say, Montana, and the demand for the product is in New York, the construction material type things are not going to be there. So yeah, it's going to come out to a real balance of the impact from an LCA basis, and then the cost of moving it. I mean, the real challenge is going to be in cost, to move materials around. And but I would also say that if you do produce materials, you can find uses locally, whether it's road building, securing your dam product, your tailings piles, or something else that materials can be deployed for. Whereas now we bring in separate materials to build the dam to hold the tailings piles. Why don't we make the dam materials out of the tailings?
Right. I'll take the next one. Are there opportunities to incorporate the minerals with sequestration CO2 into useful materials? And the answer is yes. One of the things that Doug and I have met with a number of teams and talked about, mainly mining groups, is can you pre-soften a lot of your tailings or downhole materials ahead of time to make extraction of the metals easier? So you're hitting 2 birds with 1 stone, essentially, even downhole, by processing them, but they'd have to be the right rock types. And a lot of the metals are in igneous basaltic type materials or ultramorphic species. So that should be possible. Haven't given it enough thought. We've kind of floated the idea out there. Doug, I don't know if you want to add anything to that. Maybe not. Okay.
Once I get myself off of mute, sorry, the technical challenges, the first world problems of muting yourself.
I didn't mean to put you on the spot.
Yeah, no, I think that if we can find uses for the tailings, I mean, I look at when you mineralize CO2 into these mafic or ultramafic rocks, you're making magnesium and calcium carbonates and liberating silica. There are people digging up magnesium carbonate and calcium carbonate and silica in different parts of the world. And so why not redeploy them when you can? But as Joe indicates, that's part of the problem that would be solved by using those materials. There's still a lot that of CO2 we just have to get rid of. But I think integrating in construction materials into this, either through formation of cementitious products or aggregates, is a great potential. And overall will reduce mining.
Elizabeth, if you have to turn plants to bioash to access metal oxides, do you have a sense of the life cycle assessment for the process?
Yeah, great question. So broadly speaking, I'm imagining that potentially, I'll start with, you don't necessarily need to turn the bio-ore to ash. It is possible to directly extract metals from the dried biomass. So for instance, if you want to have really high purity nickel catalysts, if that's your end goal, extracting straight from the plant could be possible. So that would be one thing. So may not necessarily need to turn to ash, but I'm curious if there is a potential possibility for turning this biomass into ash for a more efficient extraction process, and then for a more concentrated bio-ore, and then potentially with an efficient pyrolysis process, an efficient extraction process, maybe having biochar left over to store the carbon. So that would be maybe a possibility, and something that could maybe be optimized for the most carbon negative mining solution possible. So if anyone has thoughts on how that may or may not work or wants to talk more, that would be something that I'd be very interested in thinking more about.
Thanks. Halle, one more for you. What is required to make ocean mining cost competitive to conventional mining?
Well, the facetious answer is all of your ideas. Obviously, it's going to depend on the material. Some materials are going to be more economically feasible and viable than others. We've started to break down the different parts of what a process could look like. Collection is going to be key, maximizing the collection, because that has a multiplying effect on reducing the cost. Some of the ARPA-E programs give us opportunities maybe to share mooring costs, because mooring costs can be significant. So think mooring costs, think collection costs, and then finally you've got to think about the purification costs. And those four processes that I listed out: pressure, temperature, electricity, fundamental materials. We're going to need some innovation there in order to drive the costs down. Uranium got quite close to being cost competitive, and then the prices dropped significantly. Uranium prices may increase again. I think that brings uranium into the ball game. Certainly, cobalt prices are high. So I think it's going to be the more expensive metals that become economically feasible first. But that said, collection, mooring costs, and purification costs all need to be worked on. This is
Halle, I'll chime in.
A very hard problem.
I'll chime in. Halle, you touched upon it. Is a lot of these collection methods don't get one metal out of it, and I think the real key is developing processes that use everything you collect. Like a barrel of oil. If you brought oil up from the bottom of the ground just to make asphalt, you'd lose a lot of money. Yeah. How do we use everything we collect out of the seawater from a given stage to be a useful product?
Thanks for bringing that up, Doug. If you look at the people who did the work on uranium, they actually at the same time collected 3 times more vanadium and 10 times more magnesium, right? Well, magnesium is a lot cheaper than uranium, but if you're picking up 10 times more at the same time, that gives you a value proposition. If you add the uranium and the vanadium and the magnesium together, it maybe makes the economics work when previously they didn't.
Okay, thanks, Halle. Elizabeth, does the planting of bio-ore have the potential to damage the biodiversity of an environment? Will it require a similar landscape to farming?
Yes, great question. Thank you. So I'll start with the second part. So bio-ore would explicitly require a very different landscape compared to, so you would need explicitly non-arable land. It would need to be this really metal-rich, poor soil because you have about an order of magnitude more, specifically speaking about cobalt as an example, about an order of magnitude more cobalt in the surface ultramafic rock formations. And these hyperaccumulators are evolved for these environments and can accumulate that cobalt from those environments. So that would be the most efficient way of extracting your cobalt from the ground, is explicitly targeting these high metal content areas. Again, poor soil. The reason why the soil is poor, it's early in the stage of soil development. You have fresh bedrock underneath that's just barely been weathered. And so these plants have evolved for this environment, evolved to break down that rock, and evolved to take up metal. So the land area that you would need for biomining would be very different than arable land, than cropland. And the first question is the first part of that question, also a great one. So could bio or plant-based biomining impact biodiversity? So there are natural species that live on very specific, so the hyperaccumulators tend to be evolved to very, very specific areas. And oftentimes, like in one example, there's a plant that has evolved for lithium-rich soils that lives on just 10 hectares in Nevada. So you would need to make sure you're not displacing any of those species, especially since we're learning that biodiversity is potentially very important to the future of clean energy. If we can use the genes that have evolved in these very specific niche plants to do our mining for us, we should value that biodiversity and make sure we aren't displacing them as part of the process. But if we have a very well-managed lands for this purpose, I think we could definitely preserve the biodiversity while also extracting the metals. And it may be a better alternative to, say, strip mining when we're talking about preservation of these natural plants.
Okay, for Joe. In underground systems, what mineral system is most common? What carbonation reaction is most important to explore? I think because the precedent was really set well by some of the DOE's early work in Washington and the Palisades, as well as what Iceland has really been able to demonstrate quite well. And now I see the Canadians going after offshore. The classic basalts, particularly those that have a higher porosity on maybe higher glass content, might be the excellent starting point. If you can find things like dunite and serpentinite down there, those would be really great because they're quite reactive. But the basic basalt is where most people are actually targeting. It's also one of the most common species down there. Let's see. Oh, Elizabeth, you've come back to the top again. You seem to be popular. What technologies need to be developed to engineer plants for biomining purposes?
Yeah, so really broadly speaking, if we're thinking about, we want to ensure that any plant-based biomining process would be economical. So a few ways to make sure that's the case when engineering a system would be have target metals and optimize not only the concentration of metal in the plant, but potentially also the form of that metal. If we can maybe optimize that, maybe the salt that is being stored in the plant for more efficient processing down the road, that would be a very good tech to develop. We could potentially think about a crop that isolates different metals to different parts of the plant. So natural hyperaccumulators tend to accumulate one plant in one area of one metal in one part of the plant, say the leaves or the stem or the roots. But what if we could have a plant that would take up multiple metals from these metal-rich bedrocks, different metal in the stem, different metal in the roots, different metal in the leaves, and then you could have a really efficient sort of like physical separation process to process each of these metals independently. So those would just be some ideas. We could also think about how the plants could accelerate weathering as efficiently as possible. So they already create chelators and organic acids to break down the rock, but can we optimize that, that process to really make this a very economical option?
Thanks, Elizabeth. Doug, if a holistic approach to mining becomes a requirement, how does that change the economics of some of the key materials that are now currently mined? Is there a dependence on that?
It's very hard to predict. Again, we're relying on good scientists and engineers to come up with better methods to go forward. But the one thing I can say we're challenged with right now is already the quality of the ore bodies we want for the key metals for the energy transition are being depleted. So if we take a look at nickel, it's typically had in the past been mined at 2%. Weight percent, it's now dropped down below 1, and it's on its way to sub 1% within the next decade. So it's really hard to predict. And so the question is, if we can get more use out of everything, again, it's like a barrel of oil. If you can use all the fractions, each fraction by itself is not economical, but in total, they represent a lot. I think it's going to have to be the future of the way we go forward. And then I will kind of plug back into what you and I are working on, Joe. If you can get CO2 mineralization at the same time and use that CO2 credits to help dilute your fixed costs, it's going to have a huge impact. So I think we're going to find the most efficient producers are the ones who dig the less ground and get the most out of what they brought to the surface.
Thanks, Doug. Dr. King, could you talk about example strategies for accelerating in situ CO2 mineralization? Yeah, there are a number of things that people have tried, mainly in the lab. Some fairly elegant, some hard to scale. A lot of chelation science has been taking place to see which things accelerate the dissolution of the rock is usually viewed as the rate limiting step in most of these environments. So the faster you can get whatever the rock that's going to be converted into the carbonate species to dissolve faster. This is one of the reasons a lot of people pump acid down, but of course, acid and carbonates don't really mix. And so the net effect is that's great for getting faster digestion. One of the things that they have noted is that it has a high iron content, and you can pull the iron out faster. It gives you a higher porosity rate of formation, as well as sometimes they call these things, I think, wormholes that tend to form calcite and things a lot more rapidly. So I think some classical chelation chemistry is a good first step, though it has to be used on a very small scale, like a catalyst itself. Otherwise, you're going to add a lot to the cost relative to the materials you're pumping down there. I mean, the economics, there'll be a break-even point that, depending on what kind of carbon credits you get. The good thing about mineralization in general or downhole sequestration, it's depending on who does the numbers, the USGS or Iceland or the Norwegians for even their salt aquifer. This year about $17 a ton, or 8 to 13 is what the USGS predicted in a lot of their mineralizations. If you're in certain types of basalts, though, they raise that up to about $20, maybe $30, which is substantially less than what DAC is anywhere close to right now. So I think those two things, the synergy there, or the question related to co-location, become key at some point. I hope that answers your question. Let's see. Oh, we're a little bit over time, or actually on time. So I hope everyone has enjoyed this. And my colleagues and I are available. We'll be at a coffee hour tomorrow at 11 that I hope you can come to and attend. And we also are willing to meet with any or all of you at various points of the time throughout the conference or afterwards. So with that, I greatly appreciate your attendance, and I hope you found this informative. Thank you.
Thanks, Joe.
Yeah.
Thanks all.
Thank you all.
Yeah.